So in the previous section, we covered multivariable functions. And so now what we want to investigate is how we can apply things from Calc 1, like the derivative, to multivariable functions. And it turns out that you can kind of do it in the same way, but because there's more variables to deal with, we're going to have to be able to take more derivatives essentially to kind of analyze different directions that we want to go in. But before we get into the partial derivatives, let's just recap some of the rules that you're going to have to use, even if you're just doing regular or multivariable derivatives. So the first thing to remember is that d over dx just means take the derivative of. So that's what the notation is saying, is the derivative with respect to this variable x. And that's going to be important later. But all I'm saying here is the derivative of a constant by itself is equal to 0, right? And you always just have to remember that. So, and another way you can say that is the derivative of a value, say k, is equal to 0, where k is a constant or a number, right? As long as it's not the letter x, you can think of it as a number. From there, we think, okay, we could take the derivative of a single variable, and you're going to do this all the time, whether it's x, y, or z, or whatever letter you're doing. And that's just going to be 1, right? The derivative of x is just 1, right? And if you've always wondered why, it's just because x has an invisible number 1. If you do the power rule, bring down the 1 and then subtract by 1, you get x to the 0, and x to the 0 is equal to 1. So that's the justification for it. If you want to take the derivative of any power function, x to the n, so this is the power rule, that's going to be equal to, well, you bring down the n, and then you subtract by 1 on the exponent, right? So that's our power rule, right? And it works for any number n, so it doesn't have to just be nice integers. It can be decimals, real numbers, whatever you can think of. Another important one that's going to come up is potentially the derivative of e to the x. Well, that's just going to be e to the x, right? That one's just, again, one you have to memorize. And then the last one, and I would say that these are ones that you just kind of have to memorize in the sense of there is justification for what they are, but at the end of the day, just memorizing them is kind of the best way of approaching these in the beginning. So the ln of x, okay, in case that function ever comes up, it's going to be 1 over x, right? Again, these derivatives are extremely important, and they're very, useful. From there, we can say, okay, those are all just like specific functions. What are some properties of derivatives that I have to remember? The first one that you have to remember is that when you take the derivative of any function times the constant, k times f of x, essentially the constant can just be factored out and it can be ignored, right? You can just leave it in at the very end and multiply it if you need to, but it just kind of stays in the front. You don't actually have to interact with it, right? And then going on top of that, if you take the derivative of, two functions being added together, like this, really you could just take the derivatives of them individually, and there is no special rule. And one thing I want to emphasize, and this works for addition and subtraction, so plus or minus, right? All this is saying is that you don't have to make a special rule for addition and subtraction, whereas multiplication, as we're going to see in a second, we have to devise a special rule because unfortunately the derivative of f and g multiplied isn't just f prime g prime. It would be nice if that were true, but it's not. So we have to make a special rule for that. And so that rule is called the product rule. So just to remind you. And there's many variations of how this is shown. This is just the one that has stuck with me the longest and the one that I prefer. So f prime g plus f g prime, right? And over time, you can just kind of shorthand this as f prime g plus f g prime. And no matter what letters you're using, you could always write down this formula because, again, letters in mathematics are arbitrary, meaning you can really call it whatever you want. So You could technically reuse the same letters over and over again. It would just be confusing, that's all. Division has its own rule. We call that the quotient rule. So the division of two functions. And so it's very similar to the product rule if you write it this way, in that it's going to be f prime g, but instead of addition, it's going to be subtraction. So f of x prime g of x minus f of x times g prime of x all over g squared, like that. And then again, if you want to write it in a shorthand without all of the parentheses and stuff, it'd be f prime g minus fg prime over g squared. And to be clear, the condition is that g of x cannot be equal to 0, because if g of x is equal to 0, you have division by 0, which we don't appreciate in mathematics, right? And then the next important rule, and arguably one of the most important rules in mathematics of the derivatives, and that is the derivative of a composition or the derivative of a function inside of a function. And that's just going to be what we call the chain rule. So f of g of x is equal to f prime of g of x times g prime of x. And the way I always explain this is basically you're taking the derivative of the outside and then multiplying it by the derivative of the inside without touching the inside when you first start the problem, right? So that's one way of doing it. There is another interpretation that is useful, especially when you do talk about partial derivatives, and that is going to be something like df, dy du, and then du, dx, right? Where g of x is equal to u. So this is another interpretation, and we'll talk about it again later when it's necessary, but you could replace g of x with the letter u, and then this is one way of doing it. And I guess in this case, it might make more sense to use the letter f, but people like to use y, so it's the same thing. We call this Leibniz notation, and it is useful in some respects, especially when you do the chain rule of multivariable function. Like this is actually how you would do it, right? So those are the basics of the rules. And then, of course, you can add a few more with the chain rule, like for e to the x and all that. So I will do that for you. And so I'm just going to write some basic chain rules. Better word is common chain rules, because you're going to do these all the time. So common chain rules. Okay, so the first one is if you have e to some function g of x, and you're going to take the derivative of that. So e to the g of x, where it's just not the letter x, although this does technically work for that. You take the derivative of the outside. So the derivative of e to the x is just e to the x. So it would just be e to the g of x times the derivative of the inside, which is the exponent. So e to the g of x times g prime of x, right? So that's essentially what you're doing. The second one that's also very common is if you have any random function inside of a parentheses. So for example, f of x to the nth power, like that, you could just do the product rule, no, power rule, apologies, where you take the derivative of the outside, don't touch the inside, and then multiply by the derivative of the inside, right? Do you need to memorize them in this fashion? No, but I would at least memorize the g of x one, because that one's actually pretty useful. You do it all the time, especially when you're dealing with exponential functions. So, but in the long run, these are not things that you have to memorize like this exact formulation. And just to do an example, like I said, comes up all the time. If you were to take the derivative of e to the 5x, well, the derivative of e to the 5x would be just e to the 5x. The derivative of the outside is itself, times the derivative of the exponent, which would be 5, right? So then you could rewrite this as 5 e to the 5x. In fact, you could actually memorize that. So here's another common chain rule. The derivative and this is one that I've memorized, but the chain rule isn't any more challenging. AX, like that, is AE to the AX. You essentially just bring the exponent number down. And this only works for X. Like if it's X squared or anything else, that one you actually have to do the chain rule, right? And then I'll do one more for number 2. So the derivative of, in parentheses, X squared plus 3X raised to the 5th power. So essentially, you bring down the 5, don't touch the inside. You subtract the 5 by 1, and then multiply by the derivative of the inside, which would be 2x plus 3. And then you get this. And this is kind of as simplified as you could go. I mean, technically, you could distribute the 5 into the 2 and 3, but it's not necessary. So there'll be a decent amount of chain rule in your experience doing these. So, and then just to practice the product rule really quickly. So let's do an example of the product rule. So find the derivative of x squared e to the 2x. Let's just practice using the product rule and the chain rule, because in this class, but in most calculus classes, the product rule is much more favored than the quotient rule. It's because the quotient rule is just more annoying to deal with, whereas the product rule is easier, but also just more common. So maybe every once in a while you get a quotient rule problem, but at the very least, be able to do the product rule because that's kind of what's important. So for this one, we're going to do F and G, right? So we label the first one F and the second one G. It doesn't matter how you label it in terms of the first or second, just because the order for multiplication doesn't matter in the reals. And so from there, I write down my formula right above it, F prime G plus FG prime, like that. And then I just do one at a time, right? So what is the derivative of F? 2x times G, e to the 2x, plus x squared for F, and then times the derivative of G, which is 2 e to the 2x. And that's my product rule, okay? And like I said, you should at least be able to do the basics of a product rule. That way you can feel comfortable doing them. And so that kind of summarizes essentially what you learn in Calc 1 in terms of just the integration techniques. In this class, we don't cover sine and cosine really too much, so not going to be an issue unless it comes up later. But for now, we can kind of stick with those types of functions, which is polynomials and exponentials. We love polynomials and we love exponentials, okay? So now we could talk about partial derivatives. So that's going to be our next topic, which is partial derivatives. So the nice thing, but also I guess the double-edged sword of partial derivatives, if you feel comfortable with regular derivatives, partial derivatives are really the same thing. It's just the difficult part is training your brain to kind of ignore letters that are not variables for a moment, right? Because X, Y, and Z, they're all variables. But when you do a partial derivative, you kind of need to ignore 2 out of the 3 letters when you're taking a derivative, because you're basically choosing which variable you want to take the derivative with respect to. And that's the tricky part. And that takes time to get used to. So a partial derivative is a derivative of a multivariable function with respect to a certain variable. So with single variable functions, there was only one variable we were ever taking the derivative with respect to. Here, we can have as many as we want. So usually it's 2, maybe 3. And so we do have a slightly different notation. So single variables. And so essentially, if we have our original function, which is going to be f of x, which we also call y sometimes. So y equals f of x. In fact, let's just do it that way. So that's our original function. If I took the derivative, right, so the first derivative, then we end up getting like y prime equals f prime of x, right? Like that's the notation that we could use for our derivative. And again, if you want to use a slightly different notation, which is Leibniz notation, you would do dy dx, right? So that's the notation that sometimes they like to use because it's more descriptive of what's going on. For a multivariable, okay, and right now we're going to focus on just two independent variables like x and y, but you could do up to 3 or 4. 3 is probably like the maximum usually in like this kind of class. So for multivariable, our original function is no longer just y equals f of x, but rather it's going to be z is equal to, and we often like to use g, but I'll use f of x comma y, right? So that is our new function. Z is like the new y, essentially. And so if I take the first derivative, well, how would I do that? Well, you have to decide which variable you want to take the derivative with respect to. You can't just take a derivative of both variables at the same time. You kind of have to do it once at a time. So you can do x or you can do y, right? But you can't do like x and y right at the same time. So essentially, instead of using like a, dy dx, we're going to use a new notation, which we call partial. Okay, so it looks like a d, but it's kind of curved, right? So it's partial f over partial x, right? And sometimes when I write it, it will look like a d. So, but ultimately, whether you use d or partial doesn't matter. The partial symbol just tells the reader, hey, if you see this symbol, I am telling you that you have a multivariable function. You could use df dx and df dy, and it wouldn't be wrong. It just wouldn't be as descriptive. That's all. So the little partial symbol just tells the reader multivariable function in play. So how do you read this? Derivative with respect to, so with respect to x, right? It's the letter at the bottom. So that's the derivative with respect to x. And then this is the derivative with respect to y, right? Now, over time, this notation does get kind of, annoying to write all the time. So we do have a shorthand for it. And that shorthand that we can use is called subscript notation. And we just write f with a subscript x and then f with the subscript y. So what you're telling the reader here is, hey, take the partial derivative with respect to x. And that's what that means. And it's just a shorthand. Both notations are perfectly valid. I kind of go back and forth between each one depending on context. If I'm being lazy, I definitely use the subscript notation. So that's what we're going to be looking at is how do I take these derivatives? Well, the good news is it's no different than what you've been doing in the past. You just have to remember one little extra rule, and that's what we're going to talk about next. Okay, so when taking a partial derivative, with respect to any variable, all other variables will be treated as a constant. Okay, that's the key thing. When you take the derivative, partial derivative, with respect to any variable, x, y, z, doesn't matter, you must treat every other variable as if it were a constant. Okay, that's all it takes. And if you feel comfortable with that, then it ends up just being the same thing, right? So now let's do an example. So let f of x comma y be equal to 5x squared minus y cubed plus x minus 3. Compute fx, and fy. So for this one, doesn't matter what order you do it in. You could do it in the x first or the y first. So for x, which we'll do first, fx, or I guess let's do it this way. We'll do x like that. So we'll just I'm just rewriting it just so that you can kind of see how I'm doing it. X squared minus y cubed plus x minus 3. The derivative with respect to x, you don't actually have to write the parentheses when you do the subscript. It's not wrong or anything. Just people get kind of lazy about it. So you go through each term and you ask yourself this question: does it have an x term or does it not? Okay. Now, here is one thing that you need to be careful about because this happens all the time. Do not confuse partial derivatives with implicit differentiation. They are not the same thing because in implicit differentiation, you do consider the other variable because it's basically dependent on x. Now, we can incorporate implicit differentiation into this, but we don't do that right now. We're just taking straight up derivatives. So I ask myself, does it have an x? Yes. Okay, now I take the derivative normally. So I bring down the 2 and I get 10x, right? So 10x. Then I say, okay, does this have an x, the next term? And I see, nope. So then it's just going to be minus 0. Like it goes away. It just basically disappears, right? And then I go to the next term. Okay, does that have an x? Yes. Okay, what's the derivative? 1. And then I go to the next one. Does this have an x? No, it's a number. So it still would be 0 anyway. So there we go. So as long as it has an x, you take the derivative normally. If it has a y, okay, and just a y, then it becomes 0. Now the question then obviously becomes, well, what if it has x and y together in a single term? Well, we'll deal with that when we get to the next example. And so then for the y derivative, so let's do x variable. And then for the y variable, rewriting the equation. Oh yeah, I should probably simplify that. So in practice, you don't actually have to write 0. You can just basically it goes away. So rewriting the equation just so we can do it step by step. Okay, so taking the partial derivative with respect to y, I go to the first term and I say, do I see a y anywhere? No? Okay, 0. Just goes away. That's all you got to do. Then you go to the next one. Okay, does that have a y? Yep. So then I'm going to bring down the 3, subtract by 1, and I get negative 3y squared. Not too bad. Then I go to the next one. Does this have a y? No? 0. A number is just a, number, so it's just going to be 0. And so then my partial derivative is negative 3y squared. And that's how you take partial derivatives for x and y. Now, if you're wondering, what if it's a different letter like z? Same thing. You just make z your variable, and then everything else is a number. So that's the basic foundation of taking a partial derivative. You basically ignore everything except the one that matters to you in each of those derivatives. So now let's look at an example of, okay, what if the letters are being shared on a single term? So find fx and fy if f of x comma y is equal to negative 60x plus 20y plus 14xy. Okay? So now we do the same thing. So let's write this in a more step fashion now. So step 1, I'm going to compute fx. Does it matter which one you do first again? No, it doesn't matter. Okay? You can just do whichever one you like. So writing my function down, and if you write the function just like normally, f is equal to negative 60x plus 20y plus 14xy, like that. Well, the partial derivative with respect to x, so just going down one by one, does it have an x? Yep. So then take my derivative, negative 60. Then I go to the next one. Does this have an x? No. Okay, becomes 0. And then I go to the next one. Oh, does this one have an x? Yes. So here's the tricky part, unfortunately. So you got to think about it in the context of what I said earlier. When taking a partial derivative with respect to any variable, all other variables will be treated as a constant. And then if you go back to the very beginning, the derivative of a constant right here times a function is the constant times the function. Okay? So you got to pay close attention here. The derivative of 14x y is going to be 14y. And so at first glance, you might think, how is that possible, right? And so you have to think about it this way, okay? And I'm going to demonstrate another example just to illustrate that. If I asked you, hey, what's the derivative of 14x times 6? Like I just asked you to take the derivative of that. Well, you would be like, well, 14 and 6 are just numbers. So, and then x is the variable. So then 14 and 6 would be 14 times 6. X just goes away. It becomes 1, essentially, is what happens to it. It becomes 1, right? That's what happens to it. And then I get 14 times 6, which is 84, right? That's the idea. But maybe that doesn't really illustrate the picture. So what if I say, okay, instead of that, what if I say, what about 14 times A, or you know what, let me use a different letter. 14 m times x, right? Where m is a number. I tell you it's a number, right? Well, then you would say, okay, well, that's just a number times a number. So 14m, and then x becomes 1. So it's just 14m. The only difference now is it's a letter that is kind of, we're used to it being a variable, y, right? So that's the tricky part is I have to train my brain to basically ignore y in this moment and realize that, hey, it's actually just a number, right? And so just for future references, we can kind of tell ourselves that by writing this down. The derivative with respect to x, right? And I guess I should use the partial notation. So the partial derivative with respect to x of x times y is going to be y, okay? X is the variable, y is the constant, right? So that's the key. And that'll take time to get used to. So we get negative 60 plus 14y. And there we go. We have our partial derivative. So then we go to the next one. Compute fy. So for fy, we are going to basically say, okay, same idea. But now, instead of analyzing for x, we are analyzing for y. So if I take my partial derivative, one at a time, I say, does this have a y? No, it doesn't, 0. Does this have a y? Yes, it does, 20. Does this have a y? I forgot to write the x down. It does, right here. But there's an x in front of it. So how am I going to treat x? It's just a number. It's like 3, right? So then I'm going to say, okay, 14 times 3, y. Well, the y goes away and becomes 1, so 14x. And then the final answer is going to be negative 60, except it's not. And that's a common mistake people make is when you start copying your answer down, you might look at a different spot. So make sure you're paying attention to that. And it is a common trend that when you take the derivatives with respect to x or y, that the remaining letters are opposite to the derivative. Like that does happen more than you would think, right? So, and that is the biggest struggle students have with this is training their brains to ignore letters, or maybe taking the wrong derivative with the wrong letter, right? So very easily a student could have been on the first one wrote 14x because they are taking the x derivative, which means x, 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 y, 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 like you're thinking of that letter specifically, and that's just the last letter you write down. Like I've done that before myself, so you just got to be careful, right? And here's the cool part. Will you have to do like the product rule like we did in implicit differentiation? Not really. You know, like X, Y, we used to do the product rule. Product rule is a lot less prevalent. Now, can you do the product rule in any of these? Absolutely. Some problems will have the product rule, but it's not going to be like the go-to. It's actually not as common as you would think, right? So let's do another example, but now we're going to add that component of evaluation. So evaluating derivatives or partial derivatives. So first thing you need to understand in doing this is the notation, because sometimes the notation can be kind of confusing. So just to give you an idea, so if I say let f of x comma y be a function, then the partial derivative of f with respect to x, right? So partial f over partial x. If I want to evaluate this at a number, you can do this several ways, but one of the most common ways is you put a vertical line like this. Then for its partial derivatives, at a comma b, we say you would do like a comma b. Like you would actually plug it in like that. And so what that looks like in the subscript notation is you would write like fx of a comma b. All that means is take your derivative equation and plug in an x value and a y value. And then for y, it's the same thing. Vertical line a comma b. But now you just do it for the partial derivative function with respect to y. So all you're doing is just plugging the number, right? And so now let's do an example of that. Find partial f over partial x evaluated at 1, -1, and partial f over partial y evaluated at 1, -1 for f of x comma y equal to x to the -5 y squared plus xy squared plus 2xy, right? So we want to take a partial derivative and we want to plug in the number to get essentially the slope. That's what it's going to be, is a slope, right? We're going to learn that what we're finding are slopes, and you can actually do really cool things with that and analyze things like marginal cost is going to be the big one in this class. Okay, so step one is you're going to compute fx, right? The partial derivative with respect to x first, or y, doesn't matter. So just looking at it, so f is equal to, I'm just writing f without any derivatives, x to the -5 y squared plus xy squared plus 2xy. So when you first look at this, you might think, man, this derivative is going to be tough. And that's the part of your brain that you kind of have to retrain. It actually isn't as bad as you think it is, right? Because remember, anything that is not x is a number. Like you could replace all of those y terms with like the number 7, and you'd get the same answer, kind of, if you just left it alone, right? So what is the derivative of x to the -5, y squared? Well, y squared is a number, so it's just going to stay as y squared. We don't touch it. We leave it alone. And then we bring down the -5, x to the, and so -5 minus 1 y squared, like that, plus the derivative of xy squared. Well, the derivative of x is 1 times y squared, plus what's the derivative of 2xy? Well, this, so in my experience, the most commonly the most common derivative mistake people make is the x times y, where it's just plain x and y. People mess that one up all the time. They write the wrong letter down. So, and I'll make that mistake too from time to time. So the derivative with respect to x is 2y, right? And that's the partial derivative. Now we just need to simplify it. So let me just actually move this out of the way so that I have more space. So right there. And put that right there for now. And then move that up. Okay. And so simplifying it, we get negative 5x to the negative 6, y squared plus 2y, like that. And then now all you have to do is just plug in the number, right? So step 2 is just plug in 1, negative 1. And remember, the first number is always the x value, and the second number is always the y value, right? That's how we always define these ordered pairs. And so then the partial derivative at 1, negative 1, like that, again, whichever notation you prefer, just use that, is equal to negative 5 times 1 to the negative 6 power times 1 squared plus 1 squared, except it's not 1, it's negative 1. So let me fix that. And then plus 2 times negative 1. And if you plug that into your calculator correctly, the value that you will get is negative 6. So what this is going to be in the future is the slope as you move along the x-axis at this point is negative 6. What does that tell us? Well, it means the graph is going down in the x direction. Eventually, we'll be able to use it to find like maxes and mins as we did in Calc 1. All right, and so then for the third step, we're just going to compute fy. Sometimes one partial derivative is like way easier than the other. That does happen for some problems where one is like, the answer is like 3, and then the other one's like a massive algebra problem. So it's not weird if one is more difficult than the other. So just writing this down. And so if I do it with respect to y now, x to the negative 5th, that's a number in my brain. I am ignoring it. And then y squared becomes 2y. And then x is a number, so I'm ignoring it. So x, and then y squared becomes 2y. And then the derivative, and I forgot the 2 right there, so let me rewrite that. The derivative of 2xy is going to be 2, and because we're doing with y, the y goes away, and it becomes an x. And in fact, I will write the 1 down for these just so that it makes it more obvious what actually happened to it, right? It became 1, whereas everything else is just a number. And so then fy is equal to, I'm just going to move the number in front to make it look nicer. Not necessary, but does look a lot nicer. There we go. And then step 4 is plug in. So we're plugging in 1, negative 1. So fy of 1, negative 1 is equal to 2 times 1 to the negative 5th times negative 1 plus 2 times 1 times negative 1 plus 2 times 1. And if you plug that into your calculator, you should get negative 2. So that right there is going to be the slope in the y direction as we move along, right? So in this problem, we just calculated partial derivatives, and then we learned how to plug in a number, right? And that is just something you're going to do pretty much any problem that has to deal with partial derivatives in this class. So for our final example that we're going to do for a partial derivative here, until we move on to the second partial derivative, this one will require us to use the product rule and even the chain rule here. So this is a good one. So let f of x comma y be equal to x squared e to the x plus y. Find fx and fy. Find the partial derivatives, right? So over time and experience, you'll kind of see which one is like the nicer one versus which one's the uglier one. But general rule, general, behavior most people have is to do x first. So, oops, wrong step. So that's going to be find fx, right? So we're going to find fx. And so then, if we write down f is equal to x squared e to the x plus y, we recognize that there are two functions next to each other, x squared and e to the x, that both share an x, right? So that means we do have to use the product rule, okay? So I'm going to call this one here f, and I'm going to call this one here g, okay? So this product rule. And so we have f prime g plus fg prime to remind us of the product rule, which means the derivative with respect to x is going to be the derivative of f, so 2x. Now you still follow the whole, like, if there's a y, you treat it as a number, times g, e to the x plus y, and then plus x squared, and then times the derivative of e to the x plus y. So because the exponent is not just a x by itself, we have to do the chain rule. So e to the x plus y, and then we got to do the derivative of the inside. So the derivative of the inside is going to be 1 plus, what's the derivative of y? And this is where people make a mistake. They overthink it, and they forget that y is just a number. So the derivative of any number is 0. Like that, okay? And that's all you have to do. So we end up getting 2x e to the x plus y. Actually, we don't even need the parentheses there. So 2x e to the x plus y plus, and then that's just 1. So x squared e to the x plus y. And that's our partial derivative. It required us to use the product rule because there was two functions with x, not a function with x and y, but two functions that had x, and we had to deal with that. And so now we find fy. And so this one's interesting because you're thinking in your head, well, if I do the product rule there, I probably have to do the product rule now. Turns out, no, that's not how it actually ends up being. So we end up getting x squared e to the x plus y. And so x squared is just x. It's just a number to us because of the nature of y, partial derivative. So all I got to do is take the derivative of e to the x plus y. So the derivative of e to the x plus y is e to the x plus y times the derivative of the inside. So the derivative of x with respect to y is 0. And then for y, it's 1. So it just reversed. And so I get x squared e to the x plus y. And so that one ended up being a lot smoother because there was no product rule, right? And just experience and practice will make you feel more comfortable realizing which one is the variable I'm dealing with, and then which one is the constant. And once you get comfortable with that, life feels a lot better. I'm going to do one bonus example because I think it's important just to realize maybe they'll use a different letter. Like x and y, we get too comfortable with it, but what if they give you something like this? So given f of x, y, z is equal to z cubed xy plus 2xz plus, let's see, z squared, right? What if they give me that? And they say, find fx, fy, and fz. So we hadn't done z at this point, so let's just see how that goes, right? And so we're going to do fx first. So all we look for is x, right? If there is an x, I take derivative. If there's no x, it's 0. So the first one does have an x, right? So fx is equal to z cubed, it's just a number. X becomes 1, and then y is a number, right? So leave it alone. And then plus, okay, this one has an x, so 2 is a number. X becomes 1, and then z is, well, just z, right? And then the last one doesn't have an x, so that becomes 0. So we get z cubed y plus 2z, right? That's our partial derivative. We repeat the same procedure, but now for y. So I go through each one. Does it have a y? Well, the first one does have a y. It has a y at the very end, so z cubed x times 1, because y becomes 1. The next one doesn't have a y, so 0. And the last one doesn't have a y, so 0. So it's just z cubed x. That's my answer. And sometimes some will be a lot more simplified than others, and then sometimes some will be much more involved. Like the last one will be the most involved, so now we do fz. So going through each one, so z cubed will become 3z squared. X and y are just constants, so we tack them along. The next one has z, so that becomes 2x times 1, z becomes 1. And then the last one is just a z squared, so that becomes 2z. And so we get 3z squared, xy, plus 2x, plus 2z. And that is my derivative with respect to z. So again, doesn't matter what letter they use, the procedure is still the same. You just have to be comfortable using other letters besides x and y. So now we've been practicing the first derivative. What if I want to take a second derivative? What is that like? Well, unfortunately, it's a little bit more involved because in Calc 1, essentially you just take a derivative one more time. But because here you can take derivatives with one variable, like x or y, there's no reason I couldn't just change up the variable and say like, hey, what if I want to change it to x if I did y first, or if I want to change it to y if I did x first, right? Or I could just change to any other letter, right? There's no actual limitation on that. So we actually have to think about it in a different way, but thankfully it's not too bad. It's just being able to change your brain into, okay, that letter was a variable, but now it's a constant, right? So for any function f of x comma y, the second derivative is one of the following three cases. So if you took the first derivative with respect to x, you do x again. So the way we would denote that is f(x)(x). So that tells the reader, take the second derivative with respect to x again. So first with x and then x again. The partial notation will look like this. And the two, you're not squaring anything. That's just the notation that they used to use back in the day. It doesn't mean square. It just means second, right? And then this just means take derivative with respect to x and then x again, right? You do it again, one more time. Keep going. So x and x again. The second case is, okay, if I started with y, then I say do y again. So partial squared, partial f over partial y squared. And then this just means take derivative with respect to y, and then y again. Yeah, you just do it one more time. Y one more time. The third case is if you start with one letter, then you swap to the other letter, okay? Now, here's the nice thing. This is actually proven by some mathematician a long time ago. If I remember his name correctly, it was Frobenius or something along those lines. But he proved that if you start with x and swap to y, you'll get the same derivative as if you started with y and swap to x. So basically, if you start with one letter and then swap to the other, they're the same. You get the same derivative, which is really nice. It takes one option away from us that we have to consider. So the way that's written is partial squared partial f, sorry, not y, and then partial x partial y. So that's how it's written if you want to use that notation. And basically what this says is take derivative with x and then y, or y and then x, right? So you do one and then the other, okay? That's the trickiest one because if you don't quickly change your brain's, you know, in terms of like reading what's a constant and what's not a constant, it's very easy to make the wrong derivative there. So that one can be tricky, and you just got to be careful with it. So now let's just practice an example of calculating, a second derivative. And it's all just taking more derivatives, right? So the rules don't change in terms of taking a derivative itself. It's just now we got to be careful. So let f of x comma y be equal to 6x squared y. Find fxx, fyy, fxy, right? So if they ask you to find the second derivative, you will have to find the first derivative anyways, because you can't find the second derivative without knowing the first derivative, right? So that's what step one is going to be all about. So step one is to find fx and fy. Now, you can do this two ways, and this really just comes down to what works better for your brain. Some people will do like all the x stuff in one column, and then all the y stuff in one column. And then other people, like myself, I'll do the first derivatives first, and then I'll do the second derivatives second, right? It's just about keeping the work organized for yourself to be able to read it and not mix things up, essentially. So if f is equal to 6xy, sorry, 6x squared y, then fx is equal to, I bring down the 2, 12x times y. And then fy is equal to, the y becomes a 1, so 6x squared, right? So let's just move that to the middle to make it look nicer. And there it is. Those are my partial derivatives. If you're wondering, where did the 12 come from? I brought down the 2, and then 2 times 6 is 12. Why did the y stay there? Because it's a constant, right? And then if you look at the other one, what happened to the y? Well, the derivative of y is 1, so it just went away. What about 6x squared? Well, 6 is a number, and then x squared is also a number in that partial derivative because we're treating it as a constant. So then now I am going to find fxx. So now I do them individually, just so that we can clearly see what's going on. So fx is equal to 12xy. So then fxx just means, okay, you did it with x before, do it again. So x becomes a 1, y still sticks around, and so I get 12y. And as I mentioned earlier, is it common for partial derivatives of one letter not to have its own letter, but have other ones? Yes. So fxx equal 12y, that's not uncommon. You'll see that all the time. Okay, the next one is we want to find fyy. Now, does the order actually matter? No, this is just what feels the most natural for most people. So fy is going to be equal to 6x squared. And then I say, hey, there is no y term, so it's just 0, right? There is no y term, goes to 0. And then the last one is fxy, okay? Or fyx, whichever one you prefer. Sometimes one is a little bit better than the other in terms of like getting there, but they will always be equal to each other, right? So if I do fx equals 12xy, then fxy is going to be equal to 12x times 1, and so I end up getting 12x. And just to illustrate that you would get the same answer, if you did fy equal to 6x squared, and then you did fyx, you would get 12x, because you bring down the 2, right? Actually, let me show that step. 2 times 6 times x to the 2 minus 1, and so then you get 12x. And as you can see, these are both equal to the same thing. And there you go. When we get to max and min, you're going to have to calculate these three values because that's how you're going to show if something is an absolute max or an absolute min, or I guess local max, local min. And yeah, that's how you do second derivatives. So it wouldn't be Mat 211 without talking about some kind of economic topic, and in this case, it's going to be marginal cost, right? So marginal cost. So remember when you took derivatives in Calc 1, specifically like marginal revenue, marginal profit, and marginal cost, what you were investigating was the change in those values, right? How much is the revenue increasing or decreasing at a certain point? Here, we're basically doing the same thing, but now we're just looking at two variables at the same time, right? So if you're making a cake and you want to see how changing the recipe in terms of the amount of eggs or butter you use, you want to be able to calculate those different rates of change in terms of how that would affect the cost, right? If I take some butter out, is that cheaper than, say, maybe taking one egg out or something like that, right? So for a multivariable function, we can represent cost with respect to two separate inputs written as, and so it would be something like C of x comma y for cost equal to ax plus by plus, and I guess I can use a different letter here, d x times y plus maybe some like initial cost. This is just kind of like a generic form, and I'm using the letter D because C is the output variable, right? So this right here is going to represent, input 1. This right here is going to be input 2. And then this is going to be interaction between input 1 and 2. And then the last thing is just some kind of like fixed cost, right? Like there's some kind of cost associated with maybe just like making an order. Like you have to do like a minimum order. So no matter how much you order, that's like the absolute minimum, right? And then you can think of the interaction between the two where if you change one of the other ones, then that somehow impacts the other input in a way that's going to change the amount it costs, right? Maybe, for example, if you start making more of one type of object, it's much bigger than the other one, so therefore I need more space. So that's just going to cost me more because of that, or something like that, right? There is always kind of these weird interactions when you start looking at things like that. So the marginal cost is the rate of change I guess it should be more specific, is the instantaneous rate of change of an input, sorry, yeah, of an input's cost and we'll say denoted as Cx and Cy, right? So the partial derivatives with respect to x and y. So if we were to take the partial derivatives, right, of the function above, if I look at the equation, then the derivative of ax would just become a. The derivative of by would just become 0. And then the derivative of dxy would become dy because x becomes 1. And then for cy, a becomes 0, or ax becomes 0. Then we get b plus dx. And then the initial cost in both cases is 0. So this is actually the equations of your marginal cost, if it's that type of equation. Now, does marginal cost actually have to be this type of equation? No. But this is like the most generic, like linear type linear or marginal cost problem. So the values of Cx and Cy represent the increase or decrease in cost relative to x or y. And please, you really need to pay attention to this one part in the video, and that is it's the value of the increase or decrease relative to x or y if you were to make one more unit or make one less unit, but make one more unit. So if one more unit was made. So if the marginal cost is $50, when I make 50 of them, what I'm really saying is if I were to make one more, like the 51st unit was made, it would cost me about $50, right? You kind of have to move a little bit to be able to calculate that slope. So that's really the important thing, right? So if it's a positive value and if it's a negative value, positive increasing, negative decreasing, right? But people often misunderstand the derivative. It's the increase or decrease if you made one more unit, right? So that's kind of the trick to it. So let's just do an example of that next. So now let's look at an example applying this to a word problem. So find the marginal cost function of making X cups of coffee and Y pastries if their cost is modeled by this. Then determine the marginal cost of each coffee and pastry if you made 10 coffees and 15 pastries, right? So you'll never really have to make a cost model yourself, at least in this class. Maybe in business, sure, but in this class, the cost model has to be kind of given to you because it's not easy to make one. Revenue, price times quantity, that still doesn't change. And profit is still just revenue minus cost, right? So the first step that you want to do, okay, is always reread the problem. So we reread the problem. And then from there, we will find marginal cost. Now remember, there are two of them, one for x and one for y. So you're going to have to find two derivatives, right? So Cx and Cy, right? So you got to find those. I'm going to do them separately. So let's find Cx first. Cx, find marginal cost of x, which is coffee. And so Cx is going to be equal to 2 plus 0 plus 0, right? And then from there, you say, okay, I have that. And then 3, you say find cy. So cy equals, well, just looking at the y values, 0 plus 3 plus 0. And so then cy is equal to 3. And then the last part, step 4, is plug in initial values. So you got x equals 10 and y equals 15. But then you realize, hold on, I don't have anything to plug in for cx and cy. And that's true. Because logically, if you think about it, every time I sell a cup of coffee, I make $2. And every time I sell a pastry, I make $3. Or sorry, I pay $2. Not that I make, I pay $2. So the cost of each cup of coffee will always be $2, no matter how many I sell. So this is a problem where your cost function is really just flat. It's the same value, whether you make 100 pastries or you make 1,000 pastries. There is no interaction between them. So it's just going to cost the same number no matter how many you make. So then the question becomes like, okay, well, what if they do have an interaction, right? So that's what we're going to do next now. So now, suppose, okay, actually, I'll just do it on the next slide. But fundamentally, the answer is this, and we would say, if I make 10 coffees, and 15 pastries, the marginal cost to make an additional coffee is $2 and $3 for an additional pastries. And so on the exam, could they ask you a interpretation question where they make you write it out in a sentence? They could always make you do that. They love doing that, right? So you have to understand what these numbers mean. So this just means every cup of coffee I make is going to cost me $2, right? So now let's give an example of, okay, they do have some kind of interaction, right? So what would that look like? So now suppose c of x comma y is equal to 2x plus 3y equals, not equal, sorry, plus, let's say 0.210xy, right? So every time I make a pastry or a coffee, I have to label either one. So for each one, I got to label one, right? Because this is a health thing. So every time I label one, it costs me 10 cents, no matter which one I make, right? They both share that same cost. So that's kind of what the 10 cents could represent, is that if I make 10 pastries and 10 coffee cups, I got to pay 10 cents for each one I make to, label it. Then find marginal cost at 10 cups and 15 pastries. Okay. So same problem, just now we have that extra element. So again, step 1 is we're going to find CX now. So find CX. So the beginning is the same. 2x becomes 2. 3y becomes 0. However, xy doesn't become 0 because it has an x, so it's going to be 0.10 times 1 times y. So the x goes away because that's the partial derivative I'm taking it with respect to, and then y sticks around. Okay, step 2, find cy. So cy is equal to 0 plus 3 plus 0.10x, like that, right? And then step 3 is, okay, we're going to plug in. So when x is equal to 10, right? And when y is equal to 15, cy is equal to 3 plus 0.10 times x, which means 10. And so this means I have 3 plus 1. Okay. And so I get 4. And then over here, I have cx is equal to 2 plus 0.10 times 15. So cx is equal to 2 plus 1.5. And so cx is equal to 3.5. And so those are my values. Make sure you have units. So these are going to be dollars, but not just dollars. It's dollars per whatever the unit is. So dollars per cup. And then dollars, that's the wrong one, sorry, pastry. And then cup. So let's go back and make sure we correct that. So dollars per cup. Don't forget units. They could always take away points for not including units. And because it's a derivative, it's a rate, means something over something, right? You got to remember that. So how do you interpret this? If the marginal cost, let's say it that way, the marginal cost at 10 cups is 350 if I made one more cup. And technically you should say the word like is approximately 350 because it technically is an approximation, but we're not going to be super strict about it. And then here you would say the marginal cost at 15 pastries is $4 if I made one more pastry. And there you go. Or you could just combine it all into one sentence, right? The marginal cost at 10 cups and 15 pastries would be this one and this one if I made one more of that, right? And there it is. Just to be safe, we'll add the 15 cups or the 10 cups though. I just want to make sure that it's explicitly so at 10 cups and 15 pastries. So we'll just add that because technically you are inputting both parameters. So this is more of like a, just to be absolutely clear, the marginal cost at 10 cups and 15 pastries. Because although not obvious the way we write it, this technically right here is like cy of x comma y, right? And this is cx of x comma y. So they are taking two inputs. So you don't ever just plug in one number into them. So I want to make that very clear. You still have to talk about both the 10 cups and the 15 pastries in both respects. So now we're going to move on into 15.3, which is the concept of maximums and minimums.